Hi, my name is Vinicius Silva,
And I'm Ryan Miller.
and today we're bringing you the Mason bots. To begin our project, I'd like to start with the problem statement. It's to increase efficiency of brick wall construction regarding safety, profitability, and efficiency in brick-based construction projects. The context of the problem: currently, brick masonry is very expensive for construction companies, and they're very dangerous, as with any construction environment. We're also trying to reduce the amount of particulate matter and CO2 emissions in the air, hopefully help with some climate change.
Continuing our problem context here with cost, a typical 300 square foot project costs about $7,992, with a range of $6,753 to $9,223. Now, your actual price will depend on your location, your job size, conditions, and the finishing options you choose for that wall. Continuing on to safety hazards, masonry construction is recognized as one of the high-risk specialty trades with a non-fatal incident rate of 191.5 per 10,000 equivalent full-time workers and 2,640 recordable injuries. Continuing into pollution, apart from the noise, poor air quality is the most immediate pollution effect you may experience from a construction site. The main construction contaminants that spread around by wind include asbestos, carbon monoxide, carbon dioxide, and nitrogen oxides. Continuing pollution here, the production of replacement building materials depletes our natural resources and can produce air and water pollution.
So our direct customers, they're going to be the governmental councils or organizations, private construction companies, or really anybody who's willing to build a brick wall or wanting to. The indirect effects, well, the job market for individual laborers who do masonry are going to be reduced. And that's due to the decreased costs and risks that construction companies would have by using this design. Unions may have a political ally as well, who may oppose the robot swarm on the grounds of potentially higher unemployment rates. And finally, the general population will benefit from the lower building and resource costs in the form of potentially lower housing costs.
Oh, okay, cool. Design requirements. Now, our design must be able to build a brick wall. It must also meet design specifications for the dimensions of the wall. It must be able to withstand heat, cold, and moisture. It must carry 150 up to 200 feet in the air. The design must place mortar beneath and between each of the bricks. It must place bricks evenly with a set spacing between each brick, and it must be capable of delivering/placing a load of 10 bricks. Individual robot briefing. Brick and mortar bot. Responsible for orienting and laying/spreading mortar, and that is by myself, Ryan Miller.
Polar bot, it provides a quick and efficient material or resource transportation to the brick and mortar bot, and that's designed by me, Vinicius Silva. So the Holler bot will be equipped with 4 hobby motors used as rotors indicated in orange, 1 hobby motor for claw actuation indicated in green, 2 force sensors acting as stores present away switches along the undercarriage of the robot, 1 distance sensor for collision detection indicated in red, and last but not least, the Arduino board will be located on the top of the robot indicated by the color blue. The 4 rotor hobby motors will work closely with the distance sensor attached to the front, together creating a collision detection system that will run independently from the main code, while the force sensors will work primarily in conjunction with the claw actuators by verifying cargo is attached to the robot. The hub will be the primary entity sending inputs to the Hollerbot, allowing the Hollerbot to initiate its designated tasks. The Hollerbot will also send inputs to the hub to verify tasks have been completed by the robot. Some environmental inputs consist of the distance between a robot and any particular object between them, which will be picked up by the distance sensor. Another environmental input will be the force applied to the force sensor when attaching stores to the robot. When using a combination of inputs mentioned earlier, the robot will be able to verify cargo while at the same time continuously avoid collision. Once a potential collision occurs, distance sensor reads approximately 3 feet. The robot will output a signal to the hub to verify danger, as well as report it and reverse rotors for 5 seconds to avoid the collision, allowing the robot to safely and efficiently deliver the cargo. This right here is the circuit design for the Hollerbot. As you can see, the 5 hobby motors with the distance sensor and the 4 sensors attached. And this is the flow chart. When it starts off, we start with the hub activation. Has it been received? If it has, we ask, is the request for the supplies, has that been received? If it has, then it activates the rotors, it obtains the GPS location of the brick and mortar robot, and it picks up the supplies in the supply cache. Once the load is secured, it notifies the hub, it flies to the brick and mortar robot, and releases the supplies to the brick and mortar robot and notifies the hub. After that, it flies back to its resting position and it ends. We also have a sub-flow chart here for the collision detection system. What happens is when it starts, it keeps looping around, and basically it's always judging whether or not something's within 30 inches. If it is, it reverses the robot 5 seconds. And if it's not, well, then it just continues normal flight. Hi, this is the demonstration for the start off with the actual jump. All right, so now that that's out of the way here. So yes, let's get started.
All right, brick and mortar bot, sensors and actuators here. We got 2 micro servos. Those micro servos will be indicated as red. We have 1 hobby motor. That motor will be indicated as yellow. We have 1 temperature sensor. That temperature sensor is indicated as green there. We also have a force sensor. That force sensor will be indicated as orange. We have a distance sensor, which is pink. 1 Arduino in the classic Arduino blue, and we have 1 9-volt battery that will be in that gray there. All right, now this is what our robot will look like from the outside. This rectangle that is hollow, what that is going to be is a receiving station for the brick. So the brick will be placed here, and then a force sensor will be down inside this rectangle, which will allow an indication to my brick and mortar robot that those bricks have arrived and it can start its job process. All right, this here is that circuit for that brick and mortar bot. Now, as you can see, we got a soil moisture sensor here, as well as that force sensor, the hobby motor, that distance sensor, and 2 servos. So what's going to happen here is when the robot starts up, those bricks are going to be delivered to our robot. Until said bricks are delivered, this force will be at 0. Once this force gets increased, then everything starts rolling, right? Our robot will start moving forward and placing that mortar on the wall. Once that proximity alert goes off from that distance sensor there, it will reverse, and that's when it will stop laying that mortar and start laying the bricks along the wall. All right, flow chart here. So after we start, that robot activation is received. And the first thing we're worrying about here, or our first question is, does the force sensor read a force? Are the bricks in the robot? If yes, then we go on down our flow chart here. And it's, does the temperature sensor read below 150 degrees Fahrenheit? If yes, does that force sensor still read that force? If yes, then that robot places the mortar. If that force is not sensed, then we tell that central hub that we need mortar. Now, after that robot places the mortar, it will once again read that distance sensor. That distance sensor will read the end of the wall, at which time that robot will change directions and reverse to lay the bricks. Now, once it gets to the opposite end of the wall, that distance sensor will once again indicate that, and then our robot will indicate its need for increased elevation, at which time the central hub may communicate that the job is completed, and if not, then the drone will increase our elevation. Pushing off the trigger.
All right, inter-robot collaboration, fairly simple. As soon as it starts, the hub activates the brick and mortar bot, and it asks, does the brick and mortar bot have supplies? If not, the hub sends a resupply signal to the holobot. The holobot picks up the supplies, sends it back to the mortar bot, and they continue down the tree. The brick and mortar bot begins placing mortar. It retraces the wall to begin laying bricks. It elevates one brick level. Is the wall complete? No. Well, then it cycles back around. And if it is the building schematic complete? If it is, then we reach the end of the flow chart. If not, we start right back over to where whether or not the bot needs supplies. In summary, the Mason bots will lead to an increase in efficacy, profits, and reputation of governments and construction companies. It increases efficiency by reducing rate of entry and allowing the robots to operate 24/7. It increases profits by reducing overhead that the construction companies have to pay. And it increases the reputation by nearly guaranteeing project completion by the deadline established. Now, if there's one thing, I don't think I would change anything about my robot or about the project. I think I learned a lot about it, and I'm looking forward to learning a lot more. How about you, Ryan?
I also learned a great deal. Thankful for this project, honestly. One thing I might change is starting off with something maybe a bit more simplistic next time. This was a great idea, and I enjoyed jumping in the deep end with it. But at a couple of places, this project had a deep end. But it was a good time.
All right. So this concludes the project. I'll give you a quick summary of what we went over. We started the introduction by giving our problem statement and the context of the problem as well. We gave you the direct customers as well as the indirect effects. We proceeded along with the design requirements, and we went into our individual robots. After that, we hit the inter-robot collaboration, showed you how the robots work together. And now we are here at the summary. Thank you very much for your time. I appreciate it. You got anything to add, Ryan?
I hope you guys enjoyed our presentation, and in the future, I hope you guys purchase some Mason bots.